Today we're going to be dealing with a couple of new concepts. This particular chapter, carboxylic acids and their derivatives, this is how many people are taking biochem right now? Okay, so this will help you in biochem, particularly when you start talking about proteins. This chapter will be helpful. So that's one of the reasons why I've rearranged the course a little bit, is to better prepare those students that happen to be in here that are also taking biochem. So we're going to talk about carboxylic acids and their derivatives today. Again, what we're going through today is a little bit of nomenclature, a little bit of how to make some carboxylic acids, and those slides are going to be fairly quick. There's nothing on them that you haven't seen or will not be seeing again. We're going to talk about the structure and reactivity of different carboxylic acids and the different types of reactivity. We expect carboxylic acids to act as acids, that's why we call them acids, but we also need to realize, and we'll talk about, they can act as bases as well. Then there's a lot of derivatives of carboxylic acids where we replace that proton with some other group and we get what we call carboxylic acid derivatives. And all of those different derivatives undergo a specific type of reaction. They give different products, but the mechanism is almost identical for all of them, with some minor variations. And we're going to talk about that. Nucleophilic acyl substitutions is what we used to call it. Now, if I go, they call it nucleophilic addition and elimination at the acyl carbon. Those are the same things. So, and we'll talk a little bit about methods of preparing them. Again, I don't want to get too caught up in the methods of preparing them, because one of the problems with a mechanistic approach is when you get to a functional group, the methods for preparing those functional groups may be completely different mechanisms. And that's one of the reasons why we don't get too involved in the mechanisms for the preparation of these things. So here are the different, this of course is a carboxylic acid, and it has this carbonyl group with an OH bonded to the carbonyl carbon. Because this is all electron withdrawing, and we'll see why, this proton is particularly acidic, at least relative to something like an alcohol. When we replace that group with another group, we can replace it with a chloride. Notice now OH, you should be used to seeing OH minus, Cl minus. Here we've replaced it with another part of an acid. We've replaced it with what is the negative part of an alcohol or an amide. So these things are all derivatives. We've just replaced this OH with something else. Nitriles are also carboxylic acid derivatives, but they're slightly different, and so we'll deal with them a little bit separately. We're going to talk a little bit. Carboxylic acids are high boiling compounds, and the reason they're high boiling is because they have a hydrogen bond donator, and they also have hydrogen bond acceptors. Ironically, even in the gas phase, they can hydrogen bond. And in the gas phase, this species is a stable gas phase species. It's two molecules that happen to be stuck together fairly tightly, and that can exist in the gas phase. So we talk about that as being the carboxylic acid dimer, in this case specifically the acetic acid dimer. Okay, so they're high boiling because they're both hydrogen bond donators and hydrogen bond acceptors. We name them as oic acids. So for instance, this is ethanoic acid. We can have pentanoic acid. So we just put the oic acid at the end. We replace the E for ethane with oic acid. You will find a lot of common names persist in carboxylic acids. And then you will also find things, sometimes instead of propanoic acid, you might hear propionic acid or something like that. So here we have 2-hexenoic acid. The 2 is referring to the position of the double bond. So it's just oic acid. Again, there's some links to nomenclature on the Acorn site. I find it rather boring to teach, actually. It must be boring to listen to as well. When we remove the proton, we talk about the thing that's left as being the carboxylate. And so we just, instead of oic acid, we call it OAte. So here we have benzoate. This is the benzoate anion, and this is sodium benzoate because the counter cation to that anion, in this case, is sodium. Here we have potassium butanoate. They're fairly acidic, at least relative to other organic molecules, hydrogens and other organic molecules. So the pKa for water, this is controversial, by the way. Some people would argue that it should be 14. Other people argue that it's 15.7. Semantics, really. The pKa for carbonic acid, this is deceiving. It's around 7. That's actually not quite true. The pKa for carbonic acid is much lower than that. But in water, you have an equilibrium between carbon dioxide reacting with water to give carbonic acid. So this is actually an apparent pKa for carbonic acid. pKa of hydrogen fluoride is 3. Anybody know what the pKa of hydrogen chloride is? We talk about it as being a strong acid. So it's less than 0 is what we talk about because it ionizes completely in water. It's another thing in water, you can only have something ionize if it has a pKa between 0 and 14. So in water, carboxylic acids will slightly ionize. Alcohols typically will not because we'll see in a second the pKa for alcohols is quite high. So these are, barring anything else, any other kind of funny substitutions on here, electron withdrawing or electron donating groups, the pKa of carboxylic acids typically somewhere between 4 and 5. That means that they only partially ionize in water. So if we have a reaction of a carboxylic acid with water, we have this equilibrium where we have our negatively charged conjugate base, in this case acetate or ethanoate. Okay, and I'm going to most of the acetic acid would exist in this form. Only a small amount of it would actually get ionized because they're weak acids. Carboxylic acids are weak acids. We think of them as being strong acids, but that's because most of the time in organic chemistry we're comparing them to very weak acids as opposed to slightly weak acids. So we often talk about the stability of the conjugate bases when we're talking about the acidity of a compound. So there we see the conjugate base for acetic acid. We could do a similar reaction with ethanol. Now I'm going to draw a very tiny arrow there. And I drew a very tiny arrow there because this reaction virtually does not happen in water because water is not a strong enough base to pull off the proton of ethanol. It is a strong enough base to pull off the proton on a significant number of acetic acid molecules. And we see that reflected. Remember, the lower the pKa, the stronger the acid. Let's take a look at our conjugate bases. For carboxylate, I'm going to put the electrons in here. We can actually draw a resonance structure. And when we draw this resonance structure, we see that it looks a lot like this.
Should your arrows be reversed?
Which arrows? Oh, yes, you're right. Sorry. Good catch. So we can draw resonance structures for carboxylic acids where we just share that negative charge between the two oxygens. Now, if we take a look at these two resonance structures, they actually look exactly the same. The only difference is I've put the negative charge on the top oxygen here. So we would expect that these two resonance structures contribute equally to the real structure of the carboxylate anion. If we take a look at the ethoxide anion, by our rules of resonance, we cannot draw any resonance structures. So that negative charge has to exist solely on that oxygen. It can't be shared between a couple of different oxygens. And when we can disperse charge amongst the greater number of atoms, we have stabilized that compound relative to not being able to disperse that charge. So we talk about the fact that this is a better acid because we're forming a more stable anion. That reaction goes, it will be lower in energy than in this one, which we cannot stabilize. I also want you to get used to, we often talk about the strength of bases by talking about the pKa of their conjugate acids. So for instance, we'll talk about methoxide being a strong base, and we'll say, well, evidence of that is that the pKa for its conjugate acid is 16. So ethoxide is a stronger base than acetate because this is more acidic. If we have something like this compound, this is this is diisopropyl amide. Its conjugate acid would just have a proton on that nitrogen, and its pKa is around 30 something. Okay, so this is a very strong base, and in fact, in a couple of chapters, in about a month, we'll be talking about this base and using this base. The nice thing about this base is, notice we have these big isopropyl groups on it. It's a strong base, but it's not a particularly good nucleophile because of the steric hindrance. So just a foreshadowing of what's to come. So when comparing acidity, we look at the stability of the conjugate bases and see if we can disperse that charge. And with carboxylates, we can. And here we see what I've just done on the board, with the difference between acetic acid and methanol. We end up with these where we can disperse our negative charge on the acetate. So acetic acid is a better acid than ethanol. I'm sorry, I think I may have said methanol. I mean to say ethanol. So let's take a look at, here are three different compounds that contain an OH functionality. And whenever we have an OH functionality, we have a protic compound, something that can give up its proton if we have a strong enough base. Now that's true even for hydrocarbons, but hydrocarbons we don't think of as being protic because we need insanely strong bases to pull off the protons for hydrocarbons. In fact, it's so reactive, things just tend to fly apart. So we have to be careful when we're using such strong bases. But even things like alcohols, we can, even in our undergraduate labs, work with bases that would pull off that proton. It has to be fairly strong, at least relative to something to pull this off. Sodium hydroxide will pull that off quite readily. Okay? As it turns out, sodium hydroxide will pull that proton off quite readily. Sodium hydroxide will not pull off that proton very readily. So that gives us a way, and here they're talking about the acidity of carboxylic acids, phenols, and alcohols. Carboxylic acids, we've already discussed, we could draw these resonance structures. Phenol is interesting. Phenol is more acidic than cyclohexanol. Okay, they look the same. Hopefully you guys realize this is a planar molecule. This is not. This would be in some sort of chair or boat form. So these things are quite different. This is a tetrahedral carbon. This is not. This is trigonoplanar. This is sp3 hybridized, and this is sp2 hybridized. Okay, so these things are quite different. We already see that this is considerably more acidic than this. Remember with pKa, this is telling us that this is 7 orders of magnitude stronger. Okay, so the Ka for these is 10 to the minus 17 versus 10 to the minus 10. When we form this thing, the phenoxide anion, we can draw different resonance structures where we distribute that negative charge along the carbons. Okay? Now, notice I can draw a lot more resonance structures for this compound than I could for this compound. Why then is this more stable? Can anybody tell me? I can distribute the charge amongst 2 different atoms there. I'm distributing the charge amongst 2 different oxygen atoms. Here I'm distributing the charge amongst 4 different atoms, an oxygen atom, and we can actually distribute it amongst 3 of those carbons. So does anybody know why? Okay, I can distribute that charge over a greater, let's say, area. Okay, why then is the other carboxylate a better, more stable anion? And it has to do with oxygen versus carbon. Take a look. What do we see negative charges on oxygens quite often? In fact, most acids, our hydrogen, our proton is bonded to an oxygen. Oxygen is fairly electronegative, and it also easily supports a negative charge. Carbon is less electronegative, or we might say more electropositive. So carbon doesn't support a negative charge. So these 3 resonance structures would not contribute as much to the real structure as this one. If we did a charge density calculation, we would find that a large part of the negative charge exists on the oxygen. Some of it is dispersed out amongst these 3 carbons, but most of it remains on the oxygen because it's electronegative. It can support a negative charge. For this thing, we cannot draw any stable resonance structures. Remember, this is not really in a plane. This is a tetrahedral carbon, sp3 hybridized carbon, and we cannot disperse that negative charge out amongst that ring. So cyclohexanol is the weakest acid, the benzoic acid is the strongest acid, and that phenol is somewhere in between. And this is just, take a look, you're given 3 unknown samples. One is benzoic acid, one is phenol, and one is cyclohexyl alcohol. How would you distinguish them by simple chemical tests? Well, in actual fact, you might look up and you might find that if you were given this, it would actually be a powder, okay? This is also a powder, and this is probably an oil. It's probably not a powder. So that might give you a hint. But the other thing you could do is, let's react these things with sodium hydroxide. We know the pKa's for these compounds. So we would find that if we reacted these with sodium hydroxide, we should be able to get the sodium salt. And the sodium salt for this, the benzoic sodium benzoate, happens to be soluble in water. The sodium phenoxide, soluble in water. Because this one doesn't react and we have a big enough hydrocarbon portion on it, it's not soluble in water. The next thing we might do is react it instead of water. Water is a pretty, it's a decent base, but it's not a strong base. If we react it with sodium bicarbonate, it's a stronger base. It's not a very strong base, but it's stronger than water. And in fact, it's strong enough to pull the proton off of acetic acid, and we would see CO2 evolve, because once we form carbonic acid, it spontaneously breaks up into carbon dioxide and water, and we get some bubbling occurs. It's not a strong enough base to pull a proton off of the phenol, because the phenol, the pKa is around 10 or 11, and the pKa for carbonic acid is around 7. So this is not strong enough to pull that proton off, but it is pKa for the conjugate acid, which is carbonic acid, is around 7. So this base is strong enough to pull that proton off. And so we would be able to distinguish between these three by acid-base reactions. Again, keeping in mind that the more stable we can make the conjugate base, the stronger the acid will be. So in this instance, acetic acid has a pK around 4.76. Take a look at the anion. If we put an electron withdrawing group right next to where the negative charge ends up being on this carboxylate, we should withdraw electron density. We should stabilize this anion. This is a stronger acid. If we put another electron withdrawing group, same thing, it keeps going down. If we put fluorines on there, trifluoroacetic acid has a pKa somewhere around 0.2. And that's because fluorine's a very electronegative atom, the most electronegative atom, and it's pulling that electron density away through the bonds, in the bonds, because fluorine is an electron hog in a covalent bond. The fluorines or the chlorines have little small partial negative charges on them, and that pulls this negative charge all the way over there. Makes this a much more stable anion than this one that doesn't have that substitution. Now, the further we get away from the basic functionality in the anion, that effect diminishes. So for 2-chlorobutanoic acid, our pKa is 2.85. We can think of that, that's because we're stabilizing the anion. When we move that chlorine 1 bond over, the pKa of this goes up significantly. When we move it to 3 bonds over, it's 4.5. And when we move it 4 bonds over, it's starting to diminish. Remember that these are typically somewhere around 4.7, 4.8 with no substitution. Dicarboxylic acids have a tendency to have, now because you have 2 carboxylic acid functionalities, you have 2 acidic protons, and we have 2 Ka values or 2 pKa values. Oxalic acid is just C2O4H2. It's just 2 carboxylic acids bonded to each other. It's quite acidic, actually, pKa of 1.2. And that's because the carboxylic acid group is an electron withdrawing group. And when we put it onto another carboxylic acid, we withdraw the electron density away from that anion. We lower the pK of the acid. It's a better acid. Malonic acid just has a CH2 group in between them. And then adipic acid, you can see we have 4 CH2 groups in between them. And adipic acid is not really very much stronger acid than any carboxylic acid. So this is very similar to that effect we saw with chlorine, where oxalic acid has quite a low pKa, and malonic acid significantly lower than we might expect for a carboxylic acid. But as soon as we get here, that changes a little bit. Phthalic acid is a dicarboxylic acid. Notice that the second ionization is harder to do, because then we're going from something that has 1 negative charge to something that has 2 negative charges. But take a look at that pK, the second pK for oxalic acid. It's a better acid than acetic acid. Now, one of the things that you have to think about in this chapter in particular, just like water can act as an acid or a base, carboxylic acids can act as an acid or a base. And I want you to take a look, and you should realize that, because we have these oxygen atoms, and they have lone pairs of electrons. And all a base needs is to have a pair of electrons available to pull off a proton and form that bond. So we actually have two sites that could be basic, and actually they could be nucleophilic, right? They're different sites. One is kind of like an alcohol, and the other is a carbonyl oxygen. Which one of these would be more basic? Which one of these is the proton likely to go to? So if we have two choices. We can, let's take again acetic acid. And I'm going to react this. Just with some strong acid, might be sulfuric acid. It has to be a strong acid because these are not very good bases. But we're going to react it with H+. And we could react it with H+ using this pair of electrons, in which case we get this thing. Or we could react it with this pair of electrons. So notice now we have two slightly different structures. Which one of these is going to be more stable? Can we draw any resonance structures for this one? Hopefully you're looking at it. Don't forget there's lone pairs of electrons here. There's one there. Okay. We can't draw any resonance structures for this one, but we can for this one. We can just do this. And again, just like the carboxylate, we've spread that positive charge. And in fact, we can even draw another one. Where we put the lone pair of electrons there. On the carbon. And again, carbon can support a positive charge better than oxygen can for the same electronegativity arguments we used earlier. Oxygen's better at supporting negative charges. Oxonium cations, though, are quite common. So oxygen can also, we can draw positive charges on different resonance structures. So this one, we can draw 3 resonance structures and disperse that charge amongst this whole carboxylate functionality. This one we cannot. So this is a more basic site than this is, okay? Now, mechanistically, you're going to be doing a lot of reactions where you need to either protonate one of those, or your acetic acid or your carboxylic acid is going to act as a nucleophile. And remember, nucleophiles are like bases. It's because of that lone pair of electrons that it can attack something. The nice thing is, if you happen to pick the wrong one, you're actually still going to get to the same place, okay? So you don't have to worry about that too much. Most of the time, when we use it as a nucleophile, for example, it actually doesn't matter if we use this oxygen or this oxygen, we're going to end up in the same place. And that's because of the lability of the protons. Once we form these other positively charged intermediates, protons can move about to where they need to go. They tend to move about to go to the most stable structure, but that stable structure may not go on to do the next reaction. So when the proton moves to a less stable structure, that may be the one that leads to reaction. Esters, we've replaced the hydrogen with an alkyl group. We've changed the way we name it by naming this alkyl group, and then we just name the anion of the carboxylic acid. So this is methyl propanoate. So it's formed by it can be formed by reacting methanol with propanoic acid, okay? And what would you split off if you reacted methanol with propanoic acid to form this? You would get rid of some water. Here we have ethyl 2-butenoate, right? Again, the 2 is on this, it's indicating the carbon-carbon double bond, and the ethyl is indicating that this is an ethyl group. So the alkyl functionality we name is bonded to that ether-like oxygen, and then the rest of it is named as the anion of a carboxylic acid. Carboxylic anhydrides, we get those by reacting two carboxylic acids together, water comes off, and we usually just name them by dropping the word acid and adding anhydride. So this thing is ethanoic anhydride. Instead of ethanoic acid, it's ethanoic anhydride. You may also hear it called ethanoic acid anhydride. Acyl chlorides, we change, just like we did with when we have this functionality on an organic molecule, we call that the benzoyl group. And this is a chloride, so we just call it benzoyl chloride. And we can have ethanoyl chloride. And amides, we just use the word amide at the end. So there's an example of ethanamide. They're difficult to say, ethanamide. And again, we often call this relative to acetamide because the common names for carboxylic acid still kind of dominate in the nomenclature, and they are accepted by IUPAC. I'll be happy with whatever name you guys give them, as long as I know what you're talking about. Nitriles are a derivative of carboxylic acids. We're going to talk about them at the end of this chapter for the most part, and we just call this ethane nitrile. Notice it's ethane nitrile, 2 carbon atoms. We don't call it we could also call it methyl cyanide. So this is the cyanide functionality. Cyanides are nitrile, so we can also call this ethane nitrile. You know what? I'm going to skip these for now. How do we prepare carboxylic acids? They're all here. The reactions we've known. We can do a very oxidative cleavage of a carbon-carbon double bond. We have to use fairly harsh conditions, basic and heat, and then we work it up with acid. We can use ozone to clip a carbon-carbon double bond, and we have to work it up with hydrogen peroxide. So take a look at these slides. These are reactions you know. That's the Tollens test up top where we use silver to oxidize an aldehyde. Down here, we've already seen oxidation of primary alcohols and of aldehydes. So this next part, this is the important part, and we'll talk about this next class. This is one of the important reactions you're going to have to know, especially anybody who wants to get in health-related fields. This is the acyl substitution reaction or the nucleophilic addition elimination reaction. And the nice thing about this is you guys have already seen this. I don't know why our textbook uses Y for a leaving group. I like to use L, and I'll probably use L. So if we have a carboxylic acid, all we have is a leaving group here, okay? And remember, a leaving group is a nucleophile that's not very good because it prefers to leave rather than attack. And then we have some nucleophile. And we're going to use a strong nucleophile, negatively charged nucleophile. The reaction is the same as we've always seen. Nucleophile attacks the carbonyl group at the carbonyl carbon. and we just push our other electrons up onto the oxygen. Okay. Now we have this thing which we call our tetrahedral intermediate, and you'll often see that TI, tetrahedral intermediate, because we've gone from trigonoplanar carbon to tetrahedral. Our carbon has gone from sp2 hybridized to sp3 hybridized. Now this thing can reform the carbon oxygen double bond, and when it does, it has to get rid of something. And if it just gets rid of the nucleophile, it goes backwards. But if we get rid of the leaving group, we go forwards. Oops. So all we've done here is a substitution. We've substituted L for Nu, okay? It's a nucleophilic acyl substitution reaction. And just like these are in equilibrium, right? And the position of this equilibrium is going to depend. If the leaving group is a more stable anion than the nucleophile, it's going to favor that side, okay? So as you can see, what we're going to set up is a series of these derivatives where we can convert one to another. If we have a very good leaving group on our carbonyl compound, it's easy to replace it with a nucleophile. If we have a poor leaving group bonded to our carbonyl compound, it's more difficult to force it to go in that direction. So this is the general mechanism that we're going to see over and over and over again. And again, we can do this under different conditions. If I had my NuH, then it's a poor nucleophile. We can activate our carbonyl by protonating it, just like we did with aldehydes and ketones. So we're going to see this reaction a lot in this next section. The nucleophilic acyl, it occurs through this addition elimination reaction. So chlorides are good leaving groups. Anhydrides, decent leaving groups. Ethoxides, we're getting in the area of not being a very good leaving group. And amines, terrible leaving groups, okay? So these are very stable carboxylic acid derivatives, and we're happy about that because that's what most of our muscle tissue is made up, and because of that amide bond, as well as all of our proteins have a nice strong, they're amides. Esters, they're pretty strong, but they're easily hydrolyzable. Think about that as us, as beings. If our muscles were very hydrolyzable, it wouldn't be very good. We couldn't go out in the rain, we'd just dissolve, right? So that's why our muscles are made of proteins and have the amide linkage rather than esters. One reason. Acid anhydrides, they fall apart pretty easy. These things are unstable even on a mildly humid day. They will react with water. Acid chlorides, you open them up, they stink like crazy. They burn your nose because HCl gets formed, and they react with water very rapidly. It turns out we have ways of making these fairly easy. We use aggressive chemicals, but it's really nice because if we can make these, we can make any of these things. As it turns out, this one is not particularly good, especially under conditions where we're using nucleophiles. Nucleophiles are bases, and what is this thing? It's an acid. So what's going to happen when a base meets this? Most often it's going to act as an acid. We can make the conditions such that we can react at the carbonyl compound, the carbonyl carbon, but we do that by doing these under strongly acidic conditions and protonating these and activating them. Under neutral or basic conditions, this is the functionality that's going to react, okay? So that's one of the things you're going to want to remember. So what about aldehydes and ketones? Okay, these things have to leave with a negative charge. We already know that hydride and alkydes, those things with negative charge on carbon or a negatively charged hydrogen, they're very strong bases. They're horrible leaving groups. They're fantastic nucleophiles. Okay? So these things just don't leave. When they're at this point to make a decision, they always, they cannot kick off H minus or an alkyl with a minus group, minus charge on it. So they don't go in this direction. That's why this equilibrium is important for aldehydes and ketones. They can't go on further this way. The acetic acid, I'm sorry, the carboxylic acid derivatives have that option open to them. So again, there's two steps in the nucleophilic substitution: the addition of the nucleophile to the carbonyl carbon, and then the consequent elimination of the leaving group from the tetrahedral intermediate. And everything is going to be dominated by the stability here of this compound. And I think this is just saying what I've just said. Electronic factors are going to be important. So chlorine, which is somewhat electron withdrawing, actually activates that carbon electronically. The other thing that is important is steric, so that of these two compounds, this one is going to be more reactive because this has a lot of steric bulk blocking approach to the carbonyl carbon. If any nucleophile is coming from this direction, it's going to bump into those and the collision won't be successful. Whereas here, may have a successful collision, get by that tiny methyl group. Chlorine atoms are electronegative and electron withdrawing, so they suck electron density away from that already positive charge, making it even more, having a better electrophile. Now we want to be careful because with oxygen, although it's electronegative, it can contribute its lone pair of electrons in a resonance form. So quite often, and we'll talk about this next class, quite often inductively something can be electron withdrawing, but through resonance it can be electron donating, and oxygen is one of those atoms. And it's important because the p orbital that donates those electrons, the lone pair of electrons, is a 2p orbital, and carbon has 2p orbitals, so there's very good orbital overlap. Chlorine also has lone pairs of electrons, but it's further down. They're in 3p orbitals, and 3p, 2p is not good overlap energetically. So that's why they're not good at contributing their lone pairs of electrons through resonance. So this is the order of reactivity of these things. Acid chlorides are the most reactive of the carboxylic acid derivatives, followed by anhydrides. Esters, we have a lot of esters we use as solvent. Ethyl acetate is a very common organic solvent, so it's pretty stable, and it's even stable to water under, if it's not very hot and if we don't have acid or base around, esters can be quite stable, and amides are very stable. In fact, we have to go to fairly harsh conditions to hydrolyze an amide. So when we think of these things reacting with water, they can react with water or they could react with hydroxide. Hydroxide would react very quickly with this, just knock off the chloride. Fairly quickly with this, less quickly with this, but it will tend to react, and we'll look at that reaction specifically, and even less with the amides. And that's a convenient place to stop. I'll give you 2 or 3 minutes. Any questions? So I'll get you.